Oh, wow, it works. So that is at least something good. Hey, yeah. Hi, guys. I tell you what, this morning or this up until now, it has been a total nightmare. Can you actually hear me? Is that possible? Can you help me? Yes? Can you hear me? Yes. Oh, fantastic. Brilliant. Oh, I tell you what. Sometimes I wish I was my dog. They are just lying there, the sofa surface, and they are not doing anything. Jody, good question. Um, I really played around a lot with things today, so I really hope that I can do so potentially. I don't want to risk anything. I know what happened to my lovely colleague, Dr. Francis Mansfield, today. So I'm not entirely sure if I want to risk it tomorrow. Or do you think we should risk it tomorrow? What's your view? Shall we risk moving over to MS Teams tomorrow? The Mansfield incident, yes. No. I have to, guys. I have to. Otherwise, I get it in the neck. I mean, the problem is maybe start next week. Hmm. YouTube is better. I know YouTube is better, but if the Chinese, sorry, if some countries block it, I know. Do what you think it is right, Ross. Thank you. Yes, I will. What I can promise you is that I will really, really try my very best. There might be some invites over the weekend and things like that floating around, and you know, please don't get pissed off with me. It's just yes, I know, I know. That's very kind of you, Scrooge. That's lovely. Thank you. It's life. No, that's about PowerPoint. I mean, you are really lovely. I wish everybody was as accommodating and nice and kind as you are. But as somebody said, this is life, and we have to deal with it, and that's you know. But I'm pretty sure, from what I have seen, is I probably will be able to manage on Teams. And if I can manage as a non techie, then I'm sure you guys will be able to manage. And I promise you, if I can avoid PowerPoint, then I will do so. Because I have a deep loathing of PowerPoint. Do you know actually what is worse than PowerPoint? Do you know what's worse than PowerPoint? There is one thing that's worse. Yes, Prezi, Microsoft Teams. Excel. Oh, no, 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 no. Two PowerPoints, yes. What's the phrase? What's worse than a worm in an apple? No, an apple in a worm. Prezi, absolutely. I hate Prezi because it makes me feel sick, seasick. Yep, you are very close. It's absolutely diabolic, Prezi. What is worse than a worm in an apple? Well, it's half a worm in half an apple. Yummy worm. Yep. So you don't like tequila because tequila has a worm in it. Yeah, is extra protein. Yeah, probably not so much the worm's problem now that it's in half, but poor worm. What's the time? We are starting soon. Why does it have tequila worms in it? Well, actually, there is a brand of tequila. It's the mezcal tequila. Exactly. And if you, well, mezcal tequila is actually fermented from the mezcal cactus. And very often you find worms in the mezcal cactus. And sort of as a brand thing, people put that in what was originally a mistake. It's now sort of a quality brand that there is a worm in each bottle of mezcal tequila. I'm very pleased, Edith, that your internet is working. That's great. So fantastic. So let's get started. Are you ready? Yes? Let's get started with this intro to biochemistry. And again, I think it is a sort of a bit of an introduction. What will we be doing today? That's an excellent question. I don't know. Oh, sorry. No, I shouldn't say that. Um, what I want to discuss with you is really it's life. It's what are the elements of life? How do they put together? And absolutely right. Don't forget to mark your attendance on Moodle. So why I will finish early so that you then can head over to Moodle and record your attendance. Biochemistry and biological chemistry, why are they different? Well, the simple answer is biochemistry has the emphasis on the bio. Biological chemistry has the emphasis on chemistry. But we will really use these things interchangeably. So, of course, usually people start with a fantastic slide about what is life, universe, and everything. And you know the answer to life, universe, and everything. What's the answer to life, universe, and everything? It's 42. Absolutely. The answer is 42. For those of you who don't know what I'm talking about, 42, well, read the Hitchhiker's Guide to the Galaxy. The answer is 42, but nobody can really remember the question. But for us, life, of course, is based on, from what we know, life is based on carbon, isn't it? So what we would recognize as life has the elements of carbon, hydrogen, oxygen, nitrogen, what else? Phosphorus, a little bit of sulfur, and a few metals, and all these things. Maybe, just maybe, and we can discuss that in a different session, or maybe just shortly before Christmas, maybe we have to rethink what is life. What about if I told you maybe life is also based on silicon, Si, the element silicon? Why do I propose that to you? Any ideas? Why silicon? Didn't they make life silicon in the lab? No. Oh, plastic surgery. Yeah, I like that. Similar to carbon. Is it in bones? Oh, no, God, no. Please, no. Organic matter can have life. Semiconductors. Has life-making potential. Well, think about it. Where do you use silicon every day? Or silicium, not silicon, silicium. In the phone. Silicium in the phone. You're absolutely right, Sebastian. And actually, silicium is an essential part of computer chips. And computer chips, well, we are now at a time where we are developing artificial intelligence. Artificial intelligence, this is stuff where computers start to think for themselves. Right? And it's the second most common element, absolutely, in the crust. So maybe we soon come to a point where we have to rethink our definition of life. Maybe artificial intelligence from computer chips could be classified as life at one point. And in fact, last year in Saudi Arabia, there was an initiative to make some kind of ethical rules for artificial intelligence. Eva, exactly. But computers don't have consciousness. How do you know that, right? So this is really an a topical question. So when we say it's carbon based, well, we probably need to rethink at one point, right? So let's be excited about that. So we've got the elements here, and actually, here's a question. I told you we have these elements, but where do these elements actually come from? Where does carbon come from? Where does carbon come from? Space, Earth's crust, space dust, fossils, stardust. Ooh, where does it come from? The atmosphere, nuclear fusion. Dying stars. Charlotte, I love you. That is exactly what I wanted to point out. So people are going from Big Bang and things like that. Now, when we assume, when we have uh, no evidence to the contrary that there was actually that there was no Big Bang at one point. Everything started about 14.5 billion years ago, and Conrad exactly hits it on the head. There was the Big Bang, and there was only hydrogen there, hydrogen and a little bit of helium. But the first stars formed, and they burned the hydrogen, they burned the helium. And if you put two nuclei of hydrogen together like that and try to fuse them, you need a lot of energy for that, but you get also a lot of energy out. And if you do that several times, you go to helium, you then go to lithium and all these elements, and you have you produce the elements in the stars. How far can you go where you still get then some elements in the stars, in a normal star like the sun? How far can you go? Absolutely right. Iron is the largest element, and iron has only 26 protons. So that's iron. That's the heaviest element that can be produced in a star, in theory. So Conrad actually says it already in the chat. We need massive energetic events like supernova, hypernovas to produce anything larger. And we are currently, what is the element with the highest number of protons? Yes, they start to die when they have iron cores, they collapse. And these are then the supernovae. And in this case, we then produce the higher elements up there. Supernovas make uranium. Yes, what's the highest element that we are aware of? 92? Uranium? Plutonium? Now it's a synthetic element. It is called, I can't remember the name. Let me just quickly check so that I spell it correctly. Or it is called oganesson, and it has 118 protons in it. Oops. What's happening here? And it has 118 protons in it. So that's pretty heavy. But luckily, we don't have to worry about that. No, you're not supposed to know that. I just want to give you some interesting stuff. So don't panic. Yes, it is absolutely man-made. So we are basically trying to do what the supernova do naturally. But if you think about it, next time you look at a piece of gold or silver, you can truly say this stuff has been forged in the center of a sun. And I think that is just absolutely amazing. And the message that you see at the bottom of the screen that the network status is poor, don't worry about that. Right, now that was a little bit of just interesting stuff, I think. So let's, oh, for heaven's sake, what is going on here? But let's focus on the things that we are more familiar with in terms of biochemistry. And of course, we have all the neat things like, for example, nucleic acids. And we will deal with nucleic acids next week. We have proteins. We deal with proteins in weeks 3 and 4. We have lipids, and we need to discuss those. We need to discuss carbohydrates and how all these things are formed. And they are actually really the bog standard things that we are dealing with. Bog standard macromolecules that we are dealing with on a day-to-day basis as biochemists. Of course, life as we know it would not be possible without water. And that's something that we just simply have to accept as such. And when we draw water, we need to be aware how we actually can draw structures. And I think I want to spend a little bit of time on structures. For example, water would usually be drawn something like that. And very often you see it drawn in such a shape like this, where you have the different bonds. And yes, water is the most dangerous molecule because lots and lots and lots of people every year die because of water. They simply drown, floods. So it's incredibly dangerous. And what we have here is we have a very, very interesting molecule, which is, as people point out, it's not linear. Very often people make the mistake and they draw it like that. And that's not true. Water is actually bent and it has an angle of about 109 degrees or so, this angle. So it's not 180 degrees. Why do people drown? Just swim. Yeah, but if you can't swim, you drown, right? Or 104. Is it 104? 109? 109.5, something like that. So this brings us to really how do we draw molecules? And the other important thing that we need to deal with is water as such. Actually, what makes it so special is that water can form very stable connections. And another property of water is that in the solid form has a lower density than the liquid form. And that's something really interesting because that allows life as we know it to survive winters. So ice is floating on my martini. No, sorry, ice is floating on water and sort of protects life in water. And it is also a polar solvent. So what does that mean? Well, if we look at the two different components of water, we have oxygen and we've got the hydrogen. And the oxygen has something that's called higher electronegativity. Electronegativity. So oxygen has a high electronegativity. Hydrogen, not so high electronegativity. So what on earth is electronegativity? Electronegativity is just simply how much an atom would like to attract electrons. So oxygen wants electrons. It really wants electrons, and therefore, when we draw water like that, the electrons in water will be towards the oxygen. And Direct King says it really nicely. Electronegativity is the power of an atom to attract electrons towards its nucleus, in a way. Absolutely. What's the element with the highest electronegativity? Does anyone know? Fluorine, yes, absolutely. Fluorine has the highest electronegativity, which is it's a sort of an arbitrary unit. It's a unit of 4. So, oxygen attracts the electrons and therefore it becomes slightly negative because there are all the electrons hanging around the oxygen. So, but we don't still have a full negative charge, so we write this as a partial charge, and we write this with this Greek letter delta. This is a lowercase delta, and this would be negatively charged. And as a consequence, the protons or the hydrogen that we have are sort of donating their electrons here up to a certain point, and therefore they become slightly positively charged. So we've got this delta minus and delta plus for the for water. So in a way, if you like, water is a charged or partially charged compound with partial negative charge around the oxygen, and a partially positively charged around the hydrogen. If we look at, for example, a similar compound, SH, and sulfur is in the same group as oxygen, so we can draw it like that. Thank you for the likes. I've just seen it. So if we look at this compound, H2S, we have a slightly different form. H2S, what does it smell like? Not necessarily eggs. It smells of rotten eggs, actually. Yes. Because it is a product of bacterial decomposition of proteins, and they use some of the amino acids in proteins to produce this H2S. Now, when we look at H2S, S is far less electronegative than oxygen. So the sulfur does not really attract the electrons from the hydrogens, so there is no charge in there, and therefore H2S is nonpolar, whereas water is a highly polar solvent. That's absolutely fine. If people dislike it, that's totally acceptable, and I'm not cross at all. That's I'm happy with that. Better be hated than ignored. So what happens with water is that water can actually, because it is charged, because we have water like that, we can form additional sort of bonds like that. So what you see here are sort of almost, well, additional bonds, which are called hydrogen bonds. Exactly. So this is a hydrogen bond. And if you really want to understand what a hydrogen bond is, what you need is a hydrogen donor. So in this case, this here would be a hydrogen donor. And you need somebody who wants it. So in this case, this here is a hydrogen bond acceptor. And in between, you've got this poor little hydrogen. And if you like, H2S can't do that. So that's why H2S is a gas, whereas water with its hydrogen bonds is actually a liquid at room temperature. Another molecule, CO like that, carbon dioxide, again, it is to an extent polar, but we can't form any hydrogen bonds here, so this is why it's a gas. Carbon dioxide. Carbon dioxide is to a certain extent polar, but it can't form the hydrogen bonds, and that is actually why water is liquid under normal temperatures. And we will see more about hydrogen bonds when we talk about proteins and when we talk about nucleic acids. Right, so I think that's pretty nice to to see. And what we also know is that because water is such a polar substance, it is also a very good solvent for polar molecules. So if you've got anything charged in, for example, say Na plus Cl minus, table salt, then these two ions can be easily dissolved in water, in H2O. So what the water molecules do, they sit around these, and I try to indicate it like that, these water molecules sit around the ions and form a nice shell, protective shell, and they dissolve it. If you are interested in electronegativity, have a look at, I think, Boseman Science. He is doing a really good video on electronegativity. As I said, electronegativity is how much an atom really likes its electrons. So water, polar solvent for polar molecules. Or in other words, if we've got something that is not polar, that is apolar, so an apolar substance, like H2S, for example, water is not a good solvent for that. Not good solvent. And we need to be aware of that. What is, for example, this molecule? Actually, it's not absolutely correctly drawn. Is oxygen polar or apolar? It's non-polar, it's apolar, because both are really working hard to get the electrons, and there is no negative or positive charge. There is nothing like that. Would you expect oxygen to be easily dissolved in water? Absolutely right. Because this is an apolar molecule, it's not very easily, does not dissolve very well, doesn't dissolve in water. And the solubility goes down when the temperature goes up, and that is why fish, when it's really hot, they die, because they don't get enough oxygen in water. Poor fish. Okay, so not a silly question at all. So I've drawn the oxygen like that. And I assume the question refers to these things. Now, these lines here, these are called the free electron pairs. Free electron pairs. And I think maybe it might be a good idea to think a little bit about how we actually draw organic molecules that have carbon in it. So because most of the things that we are dealing with actually have carbon in it. So we have carbon. Let's move away from the water. We have carbon, and we now need to figure out how many bonds can carbon actually form. How many bonds does carbon actually form? All polar molecules dissolve in water? Yes, pretty much. 4. Okay, excellent. So carbon will always form 4 bonds. Absolutely right. How come, actually? I think you've done the biological chemistry yesterday with the different S and Ps and things like that, didn't you? Mm. Yeah, I've seen some people complaining. They have 4 bonding pairs. So let's have a look. We have usually 12,6 carbon. And let's see if we can figure out what's going on. This means we have 6 protons, and therefore we have 6 electrons in it. So how do these 6 electrons, how are they distributed? So carbon is one of the elements that always wants to achieve what is called the octet rule. Octet rule. I probably misspelled that, octet. 1 T, 2 T's. Well, you know what I mean. So it wants to achieve the octet rule. It wants to achieve noble gas status. So if we look at the periodic table, we have the first 2 electrons. So we have 2 electrons in the 1s shell. And it is usually depicted as a sort of a ball around a nucleus. So it's 1s2. 1s, oops, go back. 1s2. This means 2 electrons are fixed in the 1s shell and they are untouchable. We can't do anything with those. Then we have 4 more electrons. 4 more electrons. Sorry about that. And we need to distribute these 4 more electrons. And the next shell would be a 2s2 shell. So we have then, and this is depicted as a larger ball, usually. And this ball actually, if you think about it, it is the probability to find the electrons. So in a way, this is what is called a probability distribution. Probability distribution to find the electrons. And it looks like a ball in this case. So then we have 2 more electrons because we have 2 in the 1s2, 2 in the 2s2 shell, and we've got 2 more electrons. So we would have additional p orbitals, and we have in total space for 6 electrons in the p orbitals. That would be 2p, and we have 2, that's the level, 2p shell, and we have a total space of, we can accommodate 6 in there, but we only have 2. Now carbon can do a really neat trick. What carbon actually does, instead of saying, okay, let me draw the electron configurations here. That's the 1s shell. We have got 2 electrons, and they are usually indicated with these different spins, because the electrons can spin around. We've got the 2s configuration. We have 2 electrons in here, and then we have the p configurations. We've got basically 3 p configurations, so that's 2p. And for a normal carbon, we would have something like that. So that gives us our 6 electrons here. Sorry if you hear some noises. I'm not asleep. It's the dogs are snoring. I apologize for that. Now what carbon can do is it can actually elevate. And yes, this would be the x orbital, this would be the y orbital, and this would be the z orbital for the p. And what carbon does is it elevates these 2s to the 2p. So what we get is actually the 1s, that stays, but we shift one of the electrons into the z, and we combine what was previously our 2s. We mix them together, and now we can distribute the electrons quite nicely. So every one of these 4 now has an electron in it. So we basically elevated the 2s level to the 2p level. We mixed them, and we got a mixture of s, that's the 2s, and the 3p. And therefore, it's a sort of mixture hybridization, and it is more stable exactly when it is in this sp3 state than when it is in this weird 2s2, 2p2 state. So this is more stable than this state over here. Does that make sense? And we indicate that by saying we have 4 orbitals which are sort of a hybrid of the 1s and 3p's. So that is called hybridization. And that is why carbon will form 4 bonds. And how can we actually depict that? It's a little bit tricky because I can't draw in 3 dimensions. But this would be sort of, if we add just a hydrogen atom to it, this would be sort of a tetrahedral. tetrahedral configuration. The definition for hybridization is when you put two different orbitals together, you mix them, you put them in a blender, and you get something, some mixture, some weird concoction out of it, like this sp3 molecule. And this gives a very clear structure, if you like. It's a little bit difficult to describe, but it looks like a sort of, yeah, it looks like a tetrahedron. Why is it 3? Well, because we've got only 3 spaces, we've got only 3 p orbitals, but we mix them with the 1s, with the 2s that we got here. So that is our sp3 configuration. That's one thing. And that is results in a molecule that is not flat at all. Now we have, of course, we have another option that we can use. We can have the 1s2, and we are not going to touch the 1s2. They are staying the same. We have the 2s2. Then we have the 2p, sorry, that's the 2p orbitals with 2 in there. And we said if we mix them with the 2s, we get the sp3. But what we can do is we can actually mix only 2 of the p's. We just get sort of we mix 2 with the s, so we get, that is our s, we get p, and an extra purebred p, an extra p, where we have an electron in there. And here we've got also electrons in there. And the arrows, exactly, the arrows is how the electron actually moves around. And we can only have 2 different orientations of the electron per orbital. So this thing here would be a mixture of 1s and 2 p's plus a purebred p. So if you like, this is, in Harry Potter, you would probably call that a mudblood. sp2 plus p. Did I just say mudblood? So it is a mixture of 1s and 2 p's, and this carbon forms 3 bonds. And the easiest way to form or indicate 3 bonds, let me do this nicer here, 3 forms is flat and like a sort of product advertising Mercedes star. It's a flat molecule, but where's the third one? Where's the fourth? Where's this P? Well, this fourth one is basically coming out of the plane of the paper, like that. And it is not involved in these bonds here. These bonds are sp2, sp2, and sp2 bonds. And then we have got another one that comes out of the plane, which is the pure p bond. Does that make sense? So we've got sp2 and no, they are not slightly tetrahedral, actually, because it is symmetrical, the whole thing. sp2 is absolutely flat or planar. And the p, so if you look at it from the side, you have the carbon here, and the p orbital sticks out like that. So that's the p orbital. That's this extra p orbital that's sticking out. And of course, we can also have a situation where we mix the sp, where we mix the s with only one p, and we have p, maybe pz and py. So this would be 2 electrons are located in this hybridized one, and 2 electrons are in these. So that would give rise to sort of something like that with additional bonds like that. So something like that. Well, I shouldn't do. I should do that as a carbon. So what can these remaining p orbitals actually do? The remaining p orbitals can also overlap if there is another carbon, and we can form double and triple bonds. So if we've got an sp2 plus p, this p can overlap with another carbon, sp2. They can overlap, and we need also one of these sp2s to form a bond, and we form something that looks like that. One of these lines here, that is not a typical bond as we have seen. This is actually called a pi bond because it's made from p electrons only. Whereas these here and this one here, they are called sigma bonds because they contain an s element. So in this case, it would be sp2. Does that make sense? Is it possible to get a quadruple bond? Not as such. It would be a slightly different bond, but I like your thinking. So potentially, yeah, no, it's not. It would be a different kind of bond, but I think you are understanding the right concept. Great. Now, this is how carbon can form bonds. So we have either this form where it is sp3 tetrahedral. We might have something like that plus the pi bond. So that is sp2. That is planar, that's flat. And we could also have something like that with a triple bond. Here we have sp hybridized. One of them is a sigma bond, and 2 of them are pure p bonds. One, let's say px, one py. Does that make sense? Don't worry about the attendance. I know that you're here. And if you like it, then I know who liked it, so don't worry about it. So this is a linear molecule. One more thing that I need to do with you, if I may. Do you have a session after that? No. Can I overrun a little bit? Yep. Okay, good. Because carbon can also do something really, really interesting. It can form what is called aromatic compounds. Aromatic compounds. And we now need to sort of think about it, what this is, and people mention it. Benzene, absolutely, this is the simplest aromatic compound. Benzene. So what's happening in it? For a chemist, it doesn't mean that an aromatic compound smells good. It is basically a chemist considers an aromatic compound is something that is not immediately killing you. But it also has a specific meaning because the carbons in aromatic compounds have a particular configuration. Now, the definition of an aromatic compound is it has to be a ring. So the carbons are, just talking about smell, one of the dogs did something absolutely unspeakable. Shame on you guys. Yeah, you don't have to look at me like that. Oh, Jesus Christ almighty, that stinks. Sorry. And it stings in the eyes. Oh. Yeah. Okay. For an aromatic compound, it needs to be in a ring. So, for example, it has to have a ring structure. Usually has a hydrogen. Each carbon has a hydrogen. Like that. And all the carbons, and the ring has to be flat. This is one of the rules. It has to be a planar flat ring. So, big question from what you heard, what is the hybridization of, let's say, this carbon here? What is the hybridization? Absolutely right. Yes, this is sp2. Each single carbon is actually sp2 hybridized. And as a consequence, each carbon has an additional p bond left. Doesn't that look great? So if you look from the side in a way, what you see that for each carbon, we have additional p bonds and they can overlap. So they can form double bonds. So if you like, each carbon can form double bonds. So let's draw it. And because I'm a lazy sod, I can't be bothered to write the C's down. I just do it like that. And you know that at each corner there is a carbon in it. We can write it like that, right? Because so there is a double bond between this carbon and this carbon. There's a double bond between this carbon and this carbon. There's a double bond between this carbon and this carbon. So we've got our double bonds in there. But actually, if you think about it, this double bond, because they are all in the same plane, if you like, these p orbitals, this carbon can share this p bonds also with this one, and this can share it with this one, and this can share it with this one. So we would get a slightly different one. And I don't draw the hydrogens, so we could get something like that. And you see the double bonds can shift to the other carbon, and that leads to additional stability. Now, this is aromatic, this is benzene. And the rule to determine whether a molecule is aromatic was developed by a German chemist by the name of Hückel in, I think, 1931. Hückel said, you need to have ring. All carbons or all atoms in the ring must be sp2, and the ring must be planar. So, and the number of these pi bonds follows a rule, and this rule is 4n plus 2. And n is just simply an integer number, a whole number. So in benzene, where we have that, it is flat. We have a ring, and strictly speaking, it only works if we have a single ring. All atoms are sp2. As we said, they are all sp2. Ring is flat, and we have 2, 4, 6 bonds. And we get this if n equals 1, then we have 4 plus 2, so we've got 6 electrons in the pi bonds. So this one is an aromatic molecule. Okay, so how would we, let's have a look at this molecule. Each one of them, H, 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 H. So we have a nice molecule. Is it a ring? Yes. So this is, we have 6 carbons, 1, 2, 3, 4, 5, 6. So it would be hexane, and because it's a ring, it's cyclohexane. Cyclohexane. Yeah? Is it aromatic? Is cyclohexane aromatic? No. Absolutely right. Is it flat? Still no. It is a cycle, but it's not flat, and all the carbons are actually sp3, so it's not aromatic. Okay, let's take this guy here. So here we've got HH, here we've got H, here we've got H, here we've got 2H, 2H, HH, HH. How would you call this one? Is it a hexane or hexane? It's a cyclohexene. Hexene. Because it has this one double bond in it. Is it aromatic? How do you know it's not flat, or how do you know it's flat? Here, this carbon is sp3 because it has no pi bond, sp3. And sp3 is always tetrahedral, so it's not flat. This one here has a pi bond. It is sp2, so this part here is flat, but the rest isn't flat. So this is cyclohexane, non-aromatic. Let's do this one here. What would you call this one? It has two double bonds. It is a cyclohexadiene. And you would probably need to give the position, and in this case it would be 1 and 3. So that is the 1, 2, 3, 4 position. So that's cyclohexadiene. Is it aromatic? Is this guy aromatic? No, absolutely right. Why is it not aromatic? Because not all of them are not all of the carbons are actually sp2. This one here is sp3. And not all of them carry the pi bonds, so it can't be aromatic. Last but not least, this one here, that's our benzene, and we would call that cyclohexatriene because it has 3 double bonds. And in this case, we don't actually need to tell where these 3 double bonds are because they can actually fluctuate. As we said, they can move around, and sometimes this is just simply written like that with a ring. In it. That ring actually indicates, let me write this nicer, This ring actually indicates that there is a hole, that the electrons in there can move around. They are freely movable. And here the electrons are really not in a fixed position. They are delocalized. Delocalized. And we will do next week in one of the practicals, we will actually work with something aromatic and we will stop it from being delocalized, the electrons. So we've got delocalized electrons. Sorry, that was my artistic impression of myself. I couldn't resist. And I think at that point, we probably want to call it a day. So do you have any questions? Thank you for staying with me. That was really good. Is this on Moodle? There is quite a bit on Moodle, but I will put some links on it. That also gives you some instructions to find out whether something is aromatic or not, because we will need that. We will need that when we talk about proteins, and especially when we start to talk about the compounds of nucleic acids, which we will do tomorrow. So, thank you very much, and I will put up a link on Moodle, on YouTube, on Moodle, that shows you how you can actually get more information about that. For the time being, I need to go with the dogs now because they stink so badly. Something must have died inside them. So have a lovely evening, and I shall see you tomorrow. Take care. Bye-bye.